sorry, I will not talk about catalysis, but I will talk about our favorite catalytic material, or let's say inert catalytic material in electrochemistry, that's platinum, and specifically about how platinum degrades under different conditions. And for that I want to start with what I like to call the most often measured voltammogram in the history of electrochemistry, and that's the blank cyclic voltammogram of a polycrystalline platinum electrode. For those of you who haven't seen this, we have a region here that we consider the double layer window of polycrystalline platinum. Then we have a region that we call the hydrogen region, and the idea is that this is where hydrogen adsorbs on the electrode, and you can see that that happens in a reversible manner. We have a region that we call the oxide region, where we form various forms of oxides, and you can see that when we reduce the oxide, this is irreversible. And then the idea is if we go to more positive potentials, we evolve oxygen, and if we go to more negative potentials, we will evolve hydrogen. And this is what you will read in the textbooks. But what I will argue with you is that this is not a hydrogen region, or not just the hydrogen region, although that's not the main topic of the talk. As a result, this is not the double layer region. I will also not address that, but it's a separate talk. But what I will talk about is what happens here in this oxide region. The idea that the surface roughens, this is known, but I will want to give you a little bit more detail of what happens there exactly. So during platinum corrosion, oxide formation, and reduction of platinum oxide, we will see that the surface changes structure and roughens. And maybe not so well known is that if you go to very negative potentials, there's a phenomenon called a cathodic corrosion of platinum. And I'll elucidate that what happens, and I'll give you some insight into what happens there and what are the important intermediates. Now, to simplify things, let's go back to a very well-defined platinum surface. And so this is platinum 111, where the atoms here are arranged in this close packed fashion. And now we see that the voltammetry simplifies a lot. We have, again, a hydrogen region, which is now a single peak, if you want, and it's still reversible. And we have a region where we make OH on the surface. And you can now also see that this is reversible. It has a very special shape, known as a butterfly. Again, this is not something I will go into, but the important point is that this is now reversible on platinum 111, and I will argue with you that probably platinum 111 is the only surface on which the adsorption of OH is reversible. And then we have here something that is the double layer region, and this I actually consider as a real double layer region. Once you go and add steps and have a more structured surface, you will see that I don't think there's a true double layer window, but on platinum 111 I consider that we do have a double layer window. Now you also see these dashed lines here, and these are potentials predicted by quantum chemical calculations, or density functional theory calculations, as to where you would expect a certain coverage of hydrogen and a certain coverage of OH. And again, this is not something I will go into the details. The point I want you to take home from this is that we can calculate relatively accurately the binding energy of hydrogen and OH. We can convert that into a corresponding potential, and you see that that agrees quite well with experiments. So we can predict where we expect to form adsorbed hydrogen, where we predict adsorbed OH, and that basically means that we can calculate potentials where we expect certain surface intermediates, and then we can compare that to the voltammetry or to what we see experimentally, and then we can conclude whether we think this is a reasonable interpretation or not. Specifically here, you can also see that density functional theory calculations predict that there's going to be a window in which you do not form adsorbed hydrogen, no OH, and water is stable. And that would be a typical double layer window. So that agrees with this idea that on platinum 111 we have a double layer. Now things become a little bit more complicated when we go to more positive potentials. And this is a voltammogram from one of the papers of Granville. You recognize still here this region of hydrogen adsorption, OH adsorption. If we go to more positive potentials, you see a new peak here. And this is typically ascribed to the formation of atomic oxygen. And we're still not 100% sure if this maybe also involves the formation of subsurface oxygen. There's some X-ray spectroscopy measurements from the group of Olaf Magnussen that suggest that the surface starts buckling and that maybe oxygen goes subsurface. But if you just, after this peak, you go back, you see that there is an irreversibility here. You also see that the surface here remains the same, or it doesn't seem to change, and what we conclude from that is that the surface actually doesn't restructure if we go through this peak where we make this atomic oxygen or maybe even subsurface oxygen. So sometimes also referred to as a reversible place exchange process. Now if you go a little bit more positive, you start seeing in the Raman spectroscopy, you start seeing peaks corresponding to the formation of alpha platinum oxide. And once you make that more three-dimensional oxide, you again see that this becomes very irreversible, but now you see new peaks in the hydrogen region. And these peaks are related to the formation of step sites and defect sites. So that very strongly suggests that we are changing the platinum surface. Now traditionally, these peaks are ascribed to the adsorption of hydrogen on steps, but we have shown that this is an unlikely interpretation. What I think actually happens in these steps is that you replace adsorbed hydrogen by adsorbed OH. And so that basically means that these steps have no double layer window. The water is always dissociated either into adsorbed hydrogen, and that would be to the left of the step peak, or adsorbed OH, and that would be to the right of the step peak. And then if you go more positive, then what we think is happening here is that we oxidize the steps further, so this would be the formation of a higher oxidation state of oxygen in the step site. Now one thing that we've always been interested in is to see, okay, we can, from seeing these peaks here, we know that the surface changes. From knowing that these peaks tell us something about the geometry of the step sites, we can make some conclusions about what I think could happen, but you would actually like to see. Now before I do that, I forget one thing, and this is one thing that I wanted to show you in terms of density functional calculations. This peak here, we ascribe to atomic oxygen, so we did density functional theory calculations, and we find that we can indeed adsorb about 1/3 of a monolayer of atomic oxygen on the surface, and that is stable in the potential window where we see it in the experiment. So that seems to be a reasonable explanation, but if you want to accommodate more oxygen on the surface, it turns out that oxygen prefers to form these PTO2 stripes on the surface. And in order to accommodate these stripes, it basically means is what you lift oxygen or platinum out of the surface, you make these oxygen bridges, and then to basically fit them, you need to remove one platinum atom. And you can imagine that once you make this, that could actually be the onset of the roughening of the surface, because you basically have one platinum atom, you make a hole. When you reduce this, you're left with a hole, and I'll argue with you later that there's a barrier for the platinum diffusing back into the hole, and that basically leads to the roughening. Now we want to actually see if we could see this roughening happening, and what we did for that was simultaneous cyclic voltammetry and STM. And this is the voltammetry in the STM cell. We wanted to make sure that it looks like the way it should look like. This is not as nice as in a glass cell, but it's probably good enough. Here again you see the typical peaks, and you see how the surface changes as we go through the cycling. And before we start the experiment, we prepare the platinum 1-on-1, and it looks like this, and this image is I think about 100 by 100 nanometers. And then basically what Leon did, is the student who did this work, is that he basically takes an image here in the double layer window. He goes through one cycle, and he brings the tip back into tunneling mode. He makes an image, retracts it, goes through another cycle, brings the tip back into tunneling mode, makes another image. You can imagine that that experiment takes long. It takes about 26 hours, and then you have to repeat it 2 or 3 times to make sure that this is really, what you saw was really real. And you could argue that the thesis of Leon was based on only a single experiment and then analyzing those data. What I want to show you is what happens during the surface. After 170 cycles, what we see is the surface has completely roughened, and we form these nano islands. And actually, if you put all these images one after the other, you get a movie of the roughening. And for every image, we have the corresponding voltammetry. So now we can relate the roughening that we observe in the STM with the corresponding voltammetry that you measure of the same surface. And just to take it back, you will see that initially you start making islands, and at some point it looks like that number of islands doesn't change. It even looks like the islands do not change themselves, but you can see the voltammetry is still changing, and basically what is happening there is the islands only grow vertically, and you don't see that in this 2-dimensional projection of the STM image. But obviously you can see that in the height profiles. Now you can analyze these images and both the voltammetry as well as the STM. These peaks, we know they are related to certain configurations of step sites. We've labeled them here in A1, A2, A3, and A4, and we look at how they change as a function of cycle number. From the STM images, we can try to fit these images with a ball model of what these islands should look like, and we get a sort of average island shape and how it changes over time, and that would look something like this. So you see that initially we make a two-dimensional island, and then the island doesn't grow much anymore, at least not in the lateral directions, but you only start adding layers. So now it only grows in 3 dimensions. And then you can start counting the number of sites that you have on these islands, and you can start grouping them together and see how it relates to what you see in experiment. And this is one way of grouping them, and what we basically think is here, during the two-dimensional growth, this is the initial step sites that you see. That is this A2 peak, which is mainly 110 step sites. And most importantly, only after about 30 cycles or so, we start seeing the other peaks, and we now understand that these peaks are related to step sites that form next to narrow terraces. And basically what this means is, this essentially means that now the particle, or the nano island, only grows in the vertical direction, so it no longer grows laterally. So we have this mound formation, and the atoms forming these islands, they come basically from the vacancy. So we make these stripes of platinum oxide. We basically have to remove one platinum atom. It presumably then still hangs around on the surface. Then we reduce. That platinum atom will not go back into the original vacancy because of a barrier that is associated with hopping back into the vacancy. And so this is really at the heart of the roughening. Those atoms will find each other and will make a new island. And that is what initially happens. We have this two-dimensional growth. And then this process then repeats also on the island. And once these islands touch, then we see that only on the island itself we see this growth in the third dimension. Now we've done these experiments now also for step surface. So this is what we see on a platinum 111 surface. And what you see here, if we again go back to the electrochemistry, here you see the charge corresponding to the hydrogen UPD region as a function of cycle number. And the black line here is what we observe for platinum 111, and what we think here, this initial region here is this nucleation of vacancies and nucleation of islands and the growth. And that's basically in 2 dimensions. And then you see that there seems to be a pause in the charge corresponding to the hydrogen region, and at some point we move into this later growth, and this is what we associate with the 3-dimensional growth or the vertical growth. And what you can see, if we start from a surface that has wide terraces, 30 atoms or 10 atoms, you see that for 15, 15, 14, 5, 5, 4, we see something very, very similar. There seems to be a somewhat of a change in the initial 2-dimensional growth, but eventually they also show this 3-dimensional growth, or this lateral growth. But interestingly, if we go to surfaces with relatively narrow terraces and 2 different types of step configurations, we see that they do not seem to show this 3-dimensional growth. So they do not seem to roughen in 3 dimensions. And this, of course, then suggested that we should look at what actually happens during the STM. And this actually, I should say, this took Francesc, which was the new PhD student, almost 4 years to finally get these images. So here they are, and this is very, very new data, so we haven't analyzed them yet, but I just wanted to show them to you. So this is the oxidation reductive cycling of platinum 554, 553, and 533. What we see here for 554, you can see the step sites here, and they have a 10 atom distance, so that seems to be okay. We don't really see the formation of 2D islands. We see some step meandering, so it looks like the steps are somewhat unstable, they become wavy, but at some point you can see that we do see this 3D island growth, as the electrochemistry suggests. If we go to the 553, actually if we calculate the step-step distance, this very strongly suggests that the step is actually bunched. So 2 steps basically form a double step, and the terrace becomes twice as long. This step seems to be unstable, it meanders, and we never see any 3D island formation. And that is in agreement with what we saw in the electrochemistry. And then we go to the 553, and what is very interesting there is that we very early on we see that the straight steps are highly unstable, they meander a lot, and at some point you will see that they even change direction. And this is actually something that you can also see in the voltammetry. I didn't show you that, but originally we have a peak corresponding to a single step geometry, and as you go through the cycling it looks like all that charge is transferred to a peak of another geometry, and in the STM that is then accompanied, or on the surface is accompanied by basically a change in the direction of the step. And again, we need to analyze this. We do not know exactly what happens, but what we do think is happening is that there's a very important effect here of the oxidation of the steps themselves, and that they generate platinum atoms, and that may be a very important contribution to the dynamics of the surface. Now, in the final part of the talk, I want to go back to more negative potentials and to see what happens there. And the story how we sort of rediscovered this is related to STM. I mean, those of you who work with STM, you probably know that you make sharp platinum iridium tips. If you use a platinum iridium tip, using electrochemical etching, you apply negative, positive potentials, and then you pull them to, you basically pull the wire, and then you hope you end up with something very, very sharp. And the postdoc who did this work originally, he observed that the platinum dissolution actually didn't happen during the positive part of the potential program. It actually happened during the negative part of the potential program. And then what he started to do is look at what happens to platinum if you apply very negative potentials. Now this is a little bit extreme. You don't have to go this negative, but what you can see is if you go that to these negative potentials, you see that the surface is very strongly roughened under negative cathodic conditions. So platinum, in principle, according to the Pourbet diagram, should be cathodically protected, and you can see that what happens in reality is a very strong roughening. You can also see from the voltammetry that the surface has roughened considerably. Now here's a movie of what happens. Here's the platinum wire, here's the counter electrode. You see a lot of hydrogen forming. But if you look carefully, you see that after a while you see something else forming as well. There's a dark cloud coming off the platinum electrode at these negative potentials, and this dark cloud are aggregated nanoparticles. So at these negative potentials, platinum is actually unstable and it degrades into platinum nanoparticles. Now we were not the first to observe this. This is a relatively straightforward experiment. We realized we cannot be the first to see this. It turns out if you go back in the literature, Fritz Haber observed this already more than 100 years ago, and he called it the formation of metallic dust. Now what happens exactly is not so clear, but first let us look at, here's the wire again, and if you then zoom in, you see you generate something highly nanoporous. You can also see the nanoparticles here. You can even analyze the size distribution. It's actually a very nice way of making nanoparticles. If we add a surfactant to the solution, we can make colloidal solutions of nanoparticles, but that was not our main interest. Our main interest was to understand what was happening. This is already a somewhat older slide. I say here, this works for every metal we tried. Yes, it works for almost every metal we tried. There seems to be a few metals that do not corrode under these conditions, but for instance, gold, rhodium, they all corrode under these cathodic conditions. I write here it's not hydride formation, and that I base on the observation, and if we do this in purely acidic media, it doesn't happen. If we add a salt, and I'll show you in a minute, then the cathodic corrosion starts. What we think now is that it is hydride formation, but the dissolution needs to be stabilized by cations or irreducible catalyins in solution. So what we actually think is happening is that we make like a ternary metal hydride. And this then basically dissolves, and this then meets another water molecule. It's basically oxidized back into metallic platinum, and those act as pre-nucleation clusters for the formation of these nanoparticles. We know that organic cations also work to stabilize these pre-nucleation clusters. It's also not physical disintegration. This is also something that people have suggested, and I'll show you in a minute. This is accompanied with very regular etching patterns on the surface. Now we wanted to understand at which potential this starts, and the way we studied that is we take a polycrystalline platinum wire. We do this in very concentrated sodium hydroxide. You can do this also in acidic media, I'll show you in a minute, but you can imagine that if you evolve a lot of hydrogen, the pH close to the electrode is extremely alkaline. So this process by definition happens under very alkaline conditions. We also find that it's faster in more alkaline media. Under these conditions, at about minus 0.4 below the reversible hydrogen electrode, so that's only 400 millivolts below hydrogen evolution, we start seeing small changes in the voltammetry, and at minus 0.5 volts, so this is treatment in sodium hydroxide, and then we transfer into sulfuric acid to characterize, we see that the voltammetry changes and that this is associated to changes in the surface. And you can see those changes simply by using scanning electron microscopy. And here you see what we think is a 1-1-1 facet of the polycrystalline wire, and we make these triangular edge bits in the surface. And what we also see, if you go back to the voltammetry, we see the formation of 100 sites and 100 terraces. And that basically suggests we think that these triangular edge bits look like this. So the inside of them should have a 100 orientation. This, we think, is a 100 facet, and then the shape of the edge bit changes correspondingly, and it becomes a square shape. We've recently studied this with in situ AFM, and this experiment is somewhat similar to what Leon did with STM. So we basically take an image in the double layer window, we go to a negative potential for a certain while, and then we go back into the double layer window, because imaging, obviously, under vigorous hydrogen evolution, that's very, very difficult. What we do, if we do this experiment only in perchloric acid, we do not see changes in the surface. The surface does not corrode. If you add a salt, it corrodes. So that very strongly suggests that you have an intermediate that needs to be stabilized by sodium. But what you can see here, we start forming these these triangular edge bits. They also seem to line up on the surface, suggesting that maybe they start growing from step sites. Although it's difficult because we do not really have good atomic resolution, but that is what it suggests. And you see that at some point they start meeting, and after 15 minutes you can see that we have a relatively roughened surface, and you basically don't see the original 1-on-1 terrace anymore. You can also corrode what we call a single crystal sphere. So this is basically a sphere that or a platinum wire that we melted, and then we basically cool down very slowly, and then you get a spherical electrode, and you basically have a single crystal sphere, and then you have all the different facets in one and the same surface. And if you treat that at different potentials, you can very nicely see that the corrosion pits that you make basically reflect the atomic ordering of the facet that you're looking at. So we have square pits on the 100 facet, we have triangular pits on the 111 facet, and we have rectangular pits on the 110 facet. And interestingly, the 111 facet corrodes the fastest, and the 110 facet corrodes the slowest. And that's exactly opposite from what we observe for anodic corrosion. You can also see that for instance, this 100 facet, as you grow the square pit, at some point it becomes unstable in the 111 direction because that corrodes the fastest, and you start making these interesting diffusion limited aggregate type patterns on the surface. That says something about what is happening and the dynamics of this process, but we don't really know how to describe this at this moment. One thing that we have been interested in is to identify the intermediate that is involved in this process. And I mentioned before that in principle density functional theory could help in at least giving you an idea of what would be reasonable candidates and if they would form at the relevant potentials. So we've recently done some density functional theory calculations of 1 monolayer of hydrogen, 2 monolayers, 3, 4 monolayers of hydrogen. What we see here is that until about this potential here, 1 monolayer of hydrogen is stable. Thermodynamically speaking, you can make 2 monolayers of hydrogen at this potential window. That second monolayer goes subsurface, and it doesn't change the geometry of the surface. But once you make 3 monolayers of hydrogen, you see that the platinum starts restructuring, and you start making more like coordination type compounds, platinum hydrides on the surface. And this happens already, at least thermodynamically speaking, at potentials that agree quite well where we see the cathodic corrosion. I should say here, we did not include cations and we did not include water. Yeah, but at least it gives us a first idea that this is potentially thermodynamically possible. The other interesting thing is that from these structures, we can calculate electronic spectra. And my former postdoc, Tom Hersbach, is now in Stanford at the synchrotron, and he did some XANES spectroscopy under cathodic corrosion conditions. And the spectra that he obtains, he can now compare to theoretically calculated XANES spectra of the platinum L3 edge. And I just wanted to show you here the different spectra that we calculate. So this is a spectrum with respect to a surface that does not contain any hydrogen. And you see here the calculated spectra for 1, 2, and 3 monolayers of hydrogen with the observed spectrum at -1 volt. And what I should mention here, the theory predicts that we have a sharp negative peak and a relatively broad positive shoulder. This is very typical. We do not observe that when we oxidize platinum, and we see very different spectra. And this is also what we observe experimentally. So this, at this moment, would be the best evidence that we have that the intermediate that we make is indeed platinum hydride. Okay, finally, I showed you that there is anodic and cathodic corrosion of platinum. Anodic corrosion and restructuring happens through an oxidic intermediate. I showed you mount formation, step instability, step bunching, step meandering. I should mention that if you make thicker oxides, of course, platinum dissolves, and then you redeposit, and that also contributes to the roughening of platinum. Interestingly, if we go to negative potentials, there's another instability, which we think goes through a ternary metal hydride. This leads to anisotropic etching and nanoparticle formation. And the other thing I would like to mention is that this process is much more detrimental to platinum than anodic corrosion. So platinum dissolves really rapidly under cathodic conditions because it's not protected by anything. And here at least it's protected by an oxide layer. The sponsors and finally the people involved. Let me see, Leon was the PhD student who did the electrochemical STM. Marcel is my colleague at the physics department who built the STM and who also co-supervised Leon. Tom and Nakiran worked on the cathodic corrosion. Ian McCrum did some of the DFT calculations. Xiaoting did the AFM of the cathodic corrosion. Selwell and Hanselman also did DFT calculation. Francesca is the new student working on electrochemical STM, and Demosthenes is our colleague at SLAC in Stanford. Thank you very much for your attention.